senora, senores. That's about the only words that I know in Spanish. Oh no, there's one more word that I learned the last days, and that was decreto. And I think that is one of the reasons, and I must say I'm very amazed that in such a short time so many people could be invited and were able to come to listen to what I have to say. Before I start with my presentation, I like to say a few words about myself. My name is Franz Alfert. From nature, I'm a pyromaniac. That started at a very, very early age, that I burned our Christmas tree, and a little time later, the curtains one curtain in our house. But what I also managed is to extinguish these fires, and that, I think, prepared my path that I went into to see how you can control explosions. But of course, I still like to make explosions. And I worked for 6 years at a large test site in Norway. You will see some of the pictures that we made there. Afterwards, with the so-called German reunification, I was asked to come back to Germany to try to improve safety in Eastern German facilities where the safety standard was not very high. And therefore we tried to develop a way to make a very practical approach to existing installations. And one thing is very clear, that we have to say an existing installation cannot have the same safety level as a new one that we build from scratch. But there are many ways how we can improve safety, and one of the most important ways, of course, is the human behavior. Clean installations, so that you do not have, and we talk about dust explosions today here, if you clean everything outside of your installations, then you already have made a big step towards improving your safety. But let me start with a few things that we have at our site now, and that is, we bought in 2007 a former military site. Military site has the advantage, most often it is far away from houses, and you can make explosions. So I'm back again to what I like to do, to make explosions, study them, and try to find out how we can avoid them. What you see here is our site. It's about 30 hectares wide, with a lot of buildings in it, and we have made this area here to our test site. You also will see a few pictures and also videos on that. The site at the same time is used as a training center, and it's really the first ever training center where people train fire, they train explosions, what explosions do, get a feeling for that, and also try to see how you best avoid explosions. And so we do a lot of things here. We have firefighters there, of course. We have police there. And I will just show as an introduction a few things that we do on this site. Here you have the former boiler house that was used to heat the whole area. And we have made it to a fire training house. If you look inside, it looks like an industrial facility, which is very nice because people, when they come from companies, they feel at home. They have similar equipment in their factories, and we made it to a house where we can do fire. And we can make hell in this, and firefighters are continuously training on our site, and we have practical explosion protection seminars where people come from all over Europe mostly, but also from the US to study and see what explosions can do. And you wouldn't believe how policemen like to throw Molotov cocktails at each other and try to train how they should behave when they come into a situation where things like that are thrown against them. And so this is just as a short introduction what we do at our test site. And then I come to what we are going to talk about today, and that is to look into explosions, to look into data, how we can, what we need to know about explosions, and see how we can control explosions. And as I said in the beginning, the first step really improve safety in factories is to try to keep it clean, because otherwise you have the risk of secondary explosions, which can be very devastating. Okay, so here just a few pictures of facilities that we have investigated when an explosion happened. And due to my work on European level, so I was the chairman of the European Standardization Group for Explosion Venting. I also was invited to take part in different NFPA committees, NFPA 68, 69, 654, amongst others. And then you always come to situations like this where you see, there is a whole building blown away. We are always happy when we hear that an explosion, as for example this one in the UK, nobody was hurt or killed because it happened during lunchtime. People were at lunchtime. Now, of course, we can ask ourselves, would it have happened if people had been there? The problem is nowadays, and I assume this is similar also here in Argentina, that less and less people are in the factories. We have a lot of automation, and then, for example, we do not hear anymore that suddenly a mill is making a noise that shouldn't be there, that something seems to be loose, and so on. And therefore, in future, much more we need to have control systems that automatically control and do the right action so that we avoid that something can happen. Here you see a milling factory where, yes, the whole area of the mill blew away, but then also the house in front of it with the offices and everything went into fire. And this always tells us that there's always something that can be done, that can be improved. And we will, during this presentation, also hear how important it is to isolate. And that is something that is forgotten so often. People do explosion venting because NFPA 68 tells them, here you have to use vents on this and this volume, and we make vent design. And what we forget is that all the guidelines that we have, all the standards that we have, are based on single volume protection. So that means if we do a vent design, then this is for the volume that we design it for. But it is not going to work if the explosion travels into the vessel, if it comes from somewhere else. So therefore my advice is, if you start with explosion protection, first do explosion isolation and then try to find out where you still have an explosion risk and protect the enclosure, the vessel that you are looking at. But without explosion isolation, there is no explosion protection. Of course, tonight or this evening, I cannot address all the different pieces of equipment that you have in industry. So therefore, we just will be looking at a few of them, and that is the back filter, milling maybe a little bit connected to that, dryers, silos, and bucket elevators. I attended a meeting, an FBA meeting, I think it was 654 a few years ago, and there somebody said, okay, in small bucket elevators, we don't have explosions. So we only should go and protect the huge, big 1,000-ton elevators. The 100 or 200 ton elevators, they are too small. Unfortunately, our highest rate of explosions we have in elevators, in bucket elevators in Germany. And as a rule, our elevators are quite small. So therefore, that is not true that only huge bucket elevators can cause a problem. It's also the small ones that can cause a problem. Everybody accepts that if we have flammable liquid like acetone, that we have an explosion risk. But not everybody thinks that flour, sugar, grain dust, that is as explosible. And actually in the chemical industry with liquids like this, we nowadays very rarely have explosions. We have the explosions in the food and feed industry. And that is something we have to do something about. And so that means flour can make stronger explosions as flammable liquids. And this type of dust, not only flour, all organic dusts, they are handled in much bigger areas where many vessels are connected to each other. And also, if you handle gas or flammable liquids, very often your explosion risk is only outside of the equipment when you get a leakage or something like that. With dust, typically you have the explosion risk in the equipment. And therefore, we really need to go and look a little bit closer into this, how we can work. And most of you probably already have seen this triangle, which shows what we need to have an explosion. And that is, we need fuel, every organic material that can burn. If it is fine enough, it can explode. We need oxygen, air, and we need an ignition source. And then it depends on how things get mixed, whether we get a fire. So if we have a combustion of a fuel which is mixed with air by diffusion, then we get a fire. If we premix it and make a dust cloud, then we get an explosion. And that can be seen as an example. Okay. Okay. Here, so if we have a gas burner, then we know the flame burns on top of the gas burner, and the fuel comes from underneath, and by diffusion we get air to it and we get our flame. Oh, that's a fire. If we go and premix the same material, whether it is gas or dust, and we mix it and have it in a dust cloud, then we get an explosion. And if we then look at this curve, what happens if we have an ignition? Or if we have this cloud here with a certain volume and a certain initial pressure, normally ambient pressure, but in some factories you also have elevated pressure. And we also have to look at that and see what that then does to our explosion. If we have very strong equipment, then typically this volume here, when you ignite it, it will create 8, sometimes 10 times. If you have metal dust, it could also be 14, 15 times the initial pressure. And I say initial pressure, so that means if you have an elevated pressure of, instead of ambient, no overpressure, or if you have 1 bar overpressure and ignite it, then you get the double here. That also is sometimes forgotten, and I will come back to that when I talk about explosion isolation. If you let this cloud and you ignite it and you let it expand, then you have about 8 times the volume. Very important when you do one of the protection methods, explosion venting, because if you vent it to the outside, you get huge flames to the outside, which could make an additional risk to people, to buildings, to cause the secondary explosions. So therefore, we have to also look into that, how we can go and handle this. Now, I do not want to go too much in theory here, but this is why we have explosions. We have 2 components. I mentioned them before. We have fuel and we have oxygen. And they are at an, say, elevated level of energy. And if you add a little bit energy, then they go over the top and they start reacting with each other. And then they fall down to a less energetic product. And the energy that is being freed, that is what is causing our problems, because that is typically for organic dusts between 13 and 1600 degrees C, and that makes the pressure in our systems. I always try to explain it and then keep people remember it. I talk about here two young people, young woman and young guy. They are quite energetic, sporty, and you need to add a little bit energy to it so that they become excited enough that they go and match together. So that means it could be some dancing, it could be drinking or whatever. And when they come to this point, then they match together and they eventually fall into a much less energetic status. And that is what makes an explosion, and that is the energy that we have to handle to control explosions. Well, sometimes it won't work. Okay. So to describe then the effects of an explosion, we have to first define under what conditions this material will support combustion. We have to have a certain concentration. Do you know how high the concentration has to be to have a dust explosion? Typically we say between 30 and 60 grams of product per cubic meter. Now, how much is that? If you have a light bulb in about 2 meters distance and you cannot see this light when it is turned on, then you have the concentration that will support an explosion. Sometimes I'm getting asked against the window or against the light when you have some dust in the air. Of course, that is not good enough. Concentration is not high enough. And then, of course, we have to look at the ignition sensitivity. That means how much energy we have to add so that the material starts burning or starts exploding. And then the most important thing then afterwards is that we have to go and see the rate of and type of flame spread, and especially the pressure development and how fast it developed during the explosion. Oh, I think something. Okay. So that means what we for explosion protection, there's many other things, but what we for explosion protection need is here flammability, ignition sensitivity, and then the explosion violence. That means the rate of rise and the maximum explosion pressure that we get in order to describe what we can do. So something is happening with this one. Battery empty? I don't know. Yeah. I just, now it goes. Oh, maybe I push it too long. I'm just, yeah. Okay. Here, I do not want to go too much into detail here, but what you see on the right-hand side is dust, typically the lower explosive limit. That means the minimum concentration that you need is between 30 and 60 grams per cubic meter for all dusts, more or less. The upper explosive limit is much higher, and therefore this is typically not used in industry, because when you have a very high concentration, you could have dust settlement, and then you go into the explosive region. In certain gas situations, you can use also the upper limit, that you cannot have an explosion, but for dust we are not using that. Okay, I said you need 30 to 60 grams per cubic meter. Now what people do not realize very often is how much is that. If you have a product that has, and that is typical organic products, that have a bulk density of 500 kilos per cubic meter, and if you have then only 1 millimeter dust layer, 1 millimeter on the floor, on the tables and so on, that is not much, it's very little. But if you have 1 millimeter, then you have 500 grams per square meter. If you disperse this dust and make it 1 meter or 1 meter high, then you have 500 grams per cubic meter. That is typically the most dangerous and easiest to ignite dust concentration. So that means when you're in your factory, have 1 millimeter of dust layer on the ground, and for some reason you disperse it, then you have a very easy to ignite dust cloud. If you go the next step, you disperse it and you fill it. This room is about, I don't know, 4 meters high. If you disperse it 5 meters high, you still had 100 grams per cubic meter. That means you still would be in the explosive concentration. And that is why as I said in the beginning, the most important thing is clean the factory outside of the equipment to make sure that you do not get secondary explosions. This, of course, is not acceptable. That's ridiculous. If you see something like that in a factory with electrical engines in between and dust like that, then you should go a little bit away from that. Okay, the way we measure minimum ignition energy, because that is what we know, and we will also be talking a little bit about now how easy is dust clouds ignited and what electrostatic does, because many people talk about electrostatics, but not really having a feeling what this really is. I cannot go too deep into that, but I will spend a few words on that and see. And what you can see here is that certain dusts are quite easy to ignite, smaller than 1 millijoule for fine aluminum dust, sulfur. Organic chemicals typically are between 1 and 10 millijoules, and the most often handled products here, nettle products, they are above 10 millijoule. Depending on the moisture content, it can be much higher. And that is, I will come back to that, that is very important also for electrostatics. What we need to do and what we don't need to do. Here you see the test from our laboratory where we do this measurement for minimum ignition energy, because that is also if you have a product, but I mean for normal organic, natural organic dusts, we know it's somewhere in the range between 10 and depending on the moisture content, between 10 and 100 millijoules or even above. If you use aluminum dust, as we have done here on the right-hand side, then you see, then it can become quite strong, and even the electrodes, they just shoot out and disappear, because with very little energy, you make a very strong explosion. The reason why metal dust explosions are much more serious than the organic dust explosions is because metal dust burns at temperatures of about 3,500 degrees. Organic dust, something 1,500 degrees, so less than half of it. And that also makes a difference then in violence, in pressure, and things like that that we have to handle. Ignition temperature is another thing. So we have on one hand side, we have the minimum ignition energy. On the other side, we have the temperature at which things can ignite. That can be hot surfaces and things like that. It could also be self-heating. So if you have, and we have that in organic, with organic products, for example, if grain and things like that, if they are too wet and get into a big storage, then first you get a biological process, and afterwards it can turn into a self-heating process and you get a fire in the silo. And farmers, at least in Europe, all know if you have, if you mow grass and put it too wet into your storage, then you take a big risk that you get a fire afterwards. And that we also have had in some silo storages where you had problems, where you have problems like that. Also, if you add, and that is something that a company did in Norway, that you add some oil to it. It could be different things that fit to the product in order to reduce dusting. And they were very successful. They could go and take several filters out because they didn't have dust anymore. They had a very, very fine spray of soy oil onto the product, and then they didn't have dust anymore. What it caused was that now the self-heating temperature went down quite a bit, and so they got self-heating problems in there. in their filters, and that is not really what they wanted. So there's different ignition temperatures that we look at. It could be ignition temperature that is measured in the so-called Gottberg-Greenwald oven, where the dust cloud just falls to an outside heated pipe. And there we get one type of temperatures, but when we go into a warm storage oven, then we get much, much lower temperatures. And, but I will come back to that. And then the next thing, of course, is the flame speed, the burning velocity, or the pressure curves that are generated when we ignite it, because that we need to design the right protection method. Measured is this typically in a 20-liter sphere, or the ISO standard is a 1 cubic meter vessel, but this 20-liter test vessel gives the same result in respect to the maximum explosion pressure that we have to handle. See the maximum explosion pressure, and also the rate of rise. And the rate of rise curve, how fast the pressure goes up, that will define what kind of vent area we need to protect a certain vessel. The higher the rate of rise, the larger the vent area has to be. And what we also can see here on the right-hand side, you see 3 different volumes. You see 1 liter, 1 cubic meter, and 20 cubic meter. And what you see is that, of course, in the 1 liter vessel, the pressure is rising much faster. Okay, it's only a very little volume. And if you have a 5,000 cubic meter vessel, it becomes easier and easier to handle the explosion inside the vessel, because it takes much longer time and until you get the maximum pressure, and that is what we use for explosion venting and explosion suppression. Okay, and then you may have heard already about that. We have 3 different categories, how we categorize normally the dusts, and that is so-called ST1, ST2, or ST3 dust with a certain rate of pressure rise, and that we can use for calculating the vent area. You would typically, I think in Argentina, you mostly use NFPA standards, maybe also the European standards that then give, but they are, say, in most areas they are quite similar, because we work together with NFPA and try to match things together. Okay, so what one also has to, in certain situations, I just mentioned this shortly here, the process parameters can influence your data. That means, for example, the increase in process temperature will widen the area where the material is explosible. If we have an increase in pressure, it will increase the rate of pressure rise quite a bit, and that is something we use for explosion venting. So therefore, we have to obey. If you have a dryer or work at high temperatures, then you may have higher pressure rise in your system. Turbulence, of course, and we come back to that. Turbulence is very important for explosions. So the higher the turbulence, the stronger the explosion. And that's especially important when we have explosion transition from one vessel to the other. I don't want to go too much into this self-ignition temperature and so on. Just just have mentioned if you have a temperature measured on a hot surface, that temperature is much higher than to have it in a hot surrounding. That means in a dryer or something like that. And so that means a hot surface, then you lose your temperature to the top. And if you have your thing surrounded by heat in a dryer, then of course the ignition temperature goes down. I just jump over this. This I already have mentioned here. The thermal stability or the self-ignition temperature goes quite a bit down if you mix only small amounts of oil to your product. Then it much easier it can go and ignite. Here you see an example for brown coal. You have 4 different volumes: 1 liter, 200 liter, 1 cubic meter, and 27 cubic meters. And the self-ignition temperature for 1 liter would be 140 degrees. If you have a tank wagon full of brown coal and it's sitting in the sun, in the nice hot sun here in Argentina, it might go on fire. So therefore we always have to see the influence of temperature on something like that to make sure that we do not get into trouble there. In Europe, we look at possible ignition sources, and I would like to address a few here: hot surfaces, flames and hot gases, that means hot particles, mechanical sparks, and static electricity. Everybody really knows something about the first 3. It's obvious. If we have a hot surface and if it is too hot, then it could make the powder to brown or eventually to go on fire. And flames and hot gases, of course, that we accept that these can ignite an ignition source. Mechanical sparks, there we especially have to look for termite reactions. That means rusted steel together with aluminum, where we get very strong sparks that could cause an ignition. And then static electricity. And in the type of industry where you have elevators, chain transport, and things like that, there the relative velocity makes a bit is important. And we typically say if you have a relative speed of metal that comes into contact of less than 1 meter per second, then typically we do not consider it an ignition source. If we have a relative speed of 1 to 10 meters per second, then this could become, for easy to ignite, it could become an ignition source. For materials that are not so easy to ignite, it is not an ignition risk. But if we have transport or turning wheels that are faster than 10 meters per second, we have to consider as a very strong potential ignition source, and then we typically say then you need explosion protection. But that is something an analysis has to show: what kind of ignition sources one has in the factory, what kind of dust concentration, and also how the dust is formed, and so on. And so here you see again smaller relative velocity of rotating steel parts, smaller than 1 meter, no danger of ignition. 1 to 10 depends on the material properties, how easy to ignite, and larger 10, it has to assume that it is a potential ignition source. Just a few words to electrostatic hazards. Sometimes we call it magic static, because everybody knows something about electrostatic, and we have also in Germany, we have many explosions where people do not really find out what the ignition source was, and then it's always the magic static. But I think by now we have quite a good feeling on what electrostatic does and how it can ignite the dust cloud. So what we always have in electrostatics is that we have a charge separation that can be done by transporting things very fast, by blowing it, by having it fall down a long distance, where then things charge separates, and you can have a relaxation reaction where the different charges accumulated on the insulation and on the product, they come together again and they go to Earth. Or you could have a spark discharge, which then eventually can ignite and expose the atmosphere. But not all sparks are dangerous. So if we look at the different sparks that we have sparks, electrical sparks. They always are strong enough to ignite a dust cloud. So therefore, everything needs to be earthed. Otherwise, we have condensators that charge up, and eventually we get a discharge, a spark discharge, that will cause an ignition. So therefore, mechanical equipment needs to be earthed, always. Then we have the corona discharge and the brush discharge. And these two are, say, corona discharge cannot ignite anything. Maybe very, very easy to ignite gases, no dust. We have the brush discharge, and I think it's best if I maybe go and look a little bit into that. Corona discharge is a discharge between a non-conducting object and a very fine pointed needle. And then only a small area of this charged object will discharge, and that is so little in energy it will not ignite anything. The brush discharge. Brush discharge is a charge from a non-conducting surface, but not a very, very pointed earthed conductor, but more a round conductor. And we have some explosions that have been initiated by such a brush discharge. With brush discharge, the minimum ignition energy has to be something like 3-4 millijoules, very low. As I said before, in the food, feed industry and so on, we have minimum ignition energies quite a bit above this, and therefore brush discharge cannot ignite such clouds. And that is one very important meaning for this type of industry. If you have filters, people tend to think, if we want to improve our safety, let's go from the normal filter bags to anti-static filter bags. Anti-static filter bags are conductive so that they can get rid of the charge. The problem is, if you have an anti-static filter bag and you lose earthing of these filter bags so that the filter bags cannot discharge to earth, then they become a potential ignition source, because then you have a condensator that is charged and that then can discharge. So therefore, our recommendation is, if you have natural organic products, do not use anti-static bags, because they increase the risk for having having a spark discharge actually, and that is then causing a problem. So therefore, the advice is, if you are working in the food and feed industry with products that have a minimum ignition energy larger 10 millijoules, you use normal bags and not anti-static bags. Okay, spark discharge, I already said, spark discharge, depending on how big the piece is that is charged, they will ignite most of the dust. So I give a few curves, and you will be provided with all this data as I understand, so therefore I don't really have to go into this. One thing maybe which is very important, if you have a non-conducting layer with conducting background, and you see that sometimes, you have a plastic pipe that you use for filling a truck or a train or something like that. This plastic pipe gets damaged. And I've seen that people go and make some kind of metal sheet around it from the outside. Then you have this situation here, where you could go ahead and get a propagating brush discharge, and that is igniting everything. Okay, and then we have this cone discharge that is only in certain very special situations. So I don't think that we have to go more into detail on this here. So precautions, of course, you find a list and what one can do against this, but I think the most important message is do not use anti-static bags if you do not need them. Okay, and I think that we make a little break here. The first time is over, and then afterwards we will go into the protection methods, and I will also show a few examples on certain industrial situations, what can be done, and also describe in a few videos how an explosion looks like and what we can do against that. Okay, I thank you for the moment.